Today's topic is the differential amplifier. The function of a differential amplifier is to amplify the difference between two signals. So, the differential amplifier amplifies the difference between two signals. The need for differential amplifier arises in many physical measurements where response from DC to many megahertz is required. It is also the basic stage of an integrated operational amplifier with differential input. This figure represents a linear active device having two input terminals 1 and 2 where the signal voltage are applied that are V1 and V2, and there is one output terminal where output voltage VO is obtained. This output voltage is proportional to the difference of the applied voltages V1 and V2. Each voltage V1, V2 and VO is measured with respect to ground. In an ideal differential amplifier, the output signal should be given by VO equal to AD into V1 minus V2. V1 minus V2, we put it as VD, difference signal, difference of V1 and V2. V1 minus V2 is written as VD, VD equal to V1 minus V2. AD is gain of differential amplifier. Gain of differential amplifier AD is equal to V output upon difference in input voltages. So, for an ideal differential amplifier, output voltage V output must be equal to AD VD. It must be proportional to VD, that is difference of two input signals V1 and V2. VD is equal to V1 minus V2. It is known as the difference signal. Thus, it is seen that any signal which is common to both inputs will have no effect on the output voltage. However, a practical differential amplifier cannot be described by this equation 1, because in general the output depends not only upon the difference signal VD equal to V1 minus V2, but it also depends upon the average level, and average level is V1 plus V2 upon 2. It is the average of two input signals, which we write as VC. VC is average signal, average of two input voltages V1 and V2. So, we write VC equal to V1 plus V2 upon 2, and this average signal VC is called the common mode signal. Now we define the common mode rejection ratio. If we now introduce a figure of merit for a differential amplifier, the output of figure A can be expressed as a linear combination of the two input voltages. Output voltage can be written as linear combination of two input voltages V1 and V2. So output voltage VO is equal to A1 V1 plus A2 V2. Here A1 is the voltage amplification from input 1 to the output when input 2 is grounded, and A2 is the voltage amplification from input 2 to the output when input 1 is grounded. From equations 2 and 3 are these two equations. Equation 2 is Vd equal to V1 minus V2, while equation 3 is Vc equal to V1 plus V2 upon 2. These two equations can be solved for V1 and V2. By solving these two equations, we get the values of V1 and V2 as V1 equal to Vc plus Vd upon 2 and V2 equal to Vc minus Vd upon 2. So from equations 2 and 3 we can write the values of V1 and V2 in terms of Vc and Vd. Vc is common mode signal and Vd is difference signal. Substituting these values of V1 and V2 in equation 4, we have, this is the equation 4, VO equal to A1 V1 plus A2 V2. In this equation we substitute these two values of V1 and V2 and get VO equal to A1 into Vc plus Vd by 2 plus A2 into Vc minus Vd by 2. If we get two terms, in the first term we have Vd and in the second term we have Vc. If Vd is taken as common, we have half A1 minus A2 with it, and when Vc is taken common, we have A1 plus A2 with it. We can write it as VO equal to AD Vd plus AC Vc, where AD is equal to half A1 minus A2 and AC is equal to A1 plus A2. The term with Vd is written as AD and the term with Vc is written as AC. So AD is equal to half A1 minus A2 and AC is equal to A1 plus A2. Here AD is voltage amplification for difference signal Vd and AC is voltage amplification for common mode signal Vc. The voltage gain for the difference signal AD and that for common mode signal is AC. If we set V1 equal to 0.5 volt and V2 equal to minus 0.5 volt, then Vd, which is difference of these two signals, is equal to 1 volt, and Vc, which is the average of these two signals, is equal to 0 volt. So if we choose two input signals V1 and V2 as equal to 0.5 volt and minus 0.5 volt, then difference signal Vd becomes equal to 1 volt and common mode signal Vc becomes 0 volt. Substituting these two values in this equation 7, Vo equal to AdVd plus AcVc, we get Vo equal to Ad. So if two input signals which are applied at input terminals of differential amplifier, and these two input signals are plus 0.5 volt and minus 0.5 volt, output voltage obtained is equal to Ad, which is voltage gain for difference signal. So under these conditions, measured output voltage gives the gain for the difference signal. Similarly, if we choose V1 and V2 as equal to 1 volt both, then difference signal Vd becomes 0 volt and average signal, common mode signal Vc becomes equal to 1 volt. Then from this equation 7, Vo equal to AdVd plus AcVc, we get Vc equal to we get Vo equal to Ac, that is output voltage obtained is equal to voltage gain for common mode signal. So under these conditions, measured output voltage gives the gain for the common mode signal. Clearly we should like to have Ad large, whereas ideally Ac should equal to 0. Voltage gain for difference signal must be large, and voltage gain for average signal, that is common mode signal Ac, it must ideally be equal to 0. A quantity called the common mode rejection ratio is defined as CMRR, common mode rejection ratio. Correct it. CMMR is wrong. We write it CMRR, common mode rejection ratio. It is defined as rho equal to Ad upon Ac. There are two voltage gains, Ad voltage gain for difference signal and Ac voltage gain for common mode signal. So common mode rejection ratio CMRR is defined as rho equal to Ad upon Ac. For ideal differential amplifier, Ad must be large and Ac must be small, and ideally Ac must be equal to 0. So this common mode rejection ratio rho for an ideal differential amplifier must be equal to infinity. In practice, it is not possible that Ac is equal to 0 and rho is equal to infinity. But the differential amplifier, we required must have this common mode rejection ratio rho as very large. This common mode rejection ratio rho, which is ratio of AD and AC, it serves as a figure of merit for a differential amplifier. From equation 7, this is equation 7, VO equal to AD VD plus AC VC. In this equation, in right hand side, if we take AD VD as common, then we have expression for output voltage VO as VO equal to AD VD into 1 plus AC VC upon AD VD. This becomes equal to AD VD into 1 plus 1 upon rho into VC upon VD. Here the ratio AD upon AC is written as rho in the denominator of second term. From this equation, we see that the amplifier should be designed so that rho is large compared to the ratio of common mode signal to the difference signal. In ideal differential amplifier, we must have V output equal to AdVd, and in this equation we see that V output is not equal to AdVd. It is equal to AdVd into 1 plus 1 upon rho into Vc upon Vd. So for an ideal differential amplifier, this second term inside the bracket should be negligible, and this term will becomes negligible only when rho is large compared to the ratio Vc upon Vd. We can consider Vc upon Vd in numerator and rho in denominator. So rho must be large compared to numerator, that is Vc upon Vd, that is ratio of common mode signal to difference signal. The ammeter coupled differential amplifier. The ammeter coupled differential amplifier is shown in this figure. Here Q1 and Q2 are two symmetrical transistors which are coupled through ammeter resistance Re. Their ammeters are connected together and connected to resistance Re. Two input signals V1 and V2. Here these are Vs1 and Vs2 are applied on base of each transistor. Vs1 is applied base B1 of transistor Q1, and second signal Vs2 is applied to the base of second transistor Q2. These two signals are applied through resistances Rs, and output voltage VO is obtained between collectors of these two transistors. The circuit of this figure is an excellent differential amplifier if the ammeter resistance Re is large. if ammeter resistance Re is very large, then this circuit behaves as ideal differential amplifier. This statement can be justified as follows. If Vs1 equal to Vs2 equal to Vs, both input signals Vs1 and Vs2 are same, equal to Vs, then we have Vd equal to 0. Then difference signal Vd, which is difference of these two signals, becomes 0, and output and Vc equal to Vs. Vc is common mode signal, that is average signal. So common mode signal Vc becomes equal to Vs. Now output voltage Vo, which is equal to AdVd plus AcVc, now it becomes equal to AcVs. Now if Re equal to infinity, then because of the symmetry of the figure, we obtain IE1 equal to IE2 equal to 0. IE1 and IE2 are currents through ammeters of two transistors Q1 and Q2. IE1 is the current flowing through first transistor through ammeter of the first transistor Q1, and IE2 is the ammeter current of the second transistor Q2. If Re is very large, if Re is equal to infinity, then these two ammeter currents IE1 and IE2 becomes 0. No current flows through ammeter of each transistor, as Re ammeter resistance is infinity. Since IB2 is much less than IC2, base current in each transistor is always much less than collector current, and also base current is also much less than ammeter current. Since IB2 is much less than IC2, then IC2 also approximately becomes equal to 0, as it is equal to IE2. IC2 approximately equal to IE2, and IE2 is 0, so IC2 also becomes 0. So collector current also becomes 0, and it follows that Vo is 0. So we get output voltage equal to 0. Hence common mode gain AC equal to 0 and the common mode rejection ratio rho equal to infinity for Re equal to infinity and a symmetrical circuit. For a finite value of Re, common mode rejection ratio rho increases with increase in Re. There are, however, practical limitations on the magnitude of Re. We cannot increase the value of Re up to any limit. There are certain limitations, and it cannot be increased above certain limit. So for an ideal differential amplifier, we keep Re ammeter resistance as large as possible, which keeps common mode rejection ratio rho very large. There is one numerical example. First part A. Consider two set of input signals. First set is V1 equal to plus 50 microvolt and V2 equal to minus 50 microvolt, and second set is V1 equal to plus 1050 microvolt and V2 equal to 950 microvolt. If the common mode rejection ratio rho is 100, calculate the percentage difference in output voltage from these two sets. In next part, repeat part A if rho equal to 10,000. So in the first case, we have difference voltage Vd, which is equal to V1 minus V2, difference of two voltages. It is equal to 100 microvolt, and common mode signal Vc equal to V1 plus V2 by 2, which is equal to 0. And output voltage Vo is equal to Ad Vd into 1 plus 1 upon rho Vc upon Vd. As Vc is equal to 0, second term inside the bracket becomes 0, and we have output voltage Vo equal to 100 Ad microvolt. Vd is 100 microvolt. So we get output voltage Vo equal to 100 Ad microvolt. In the second case, when V1 equal to plus 1050 microvolt and V2 equal to 950 microvolt, we get the difference voltage Vd equal to V1 minus V2, which is equal to 100 microvolt, and average voltage, which is common mode signal Vc, which is equal to V1 plus V2 upon 2. Now it becomes equal to 1000 microvolt. Substituting these two values in this relation, Vo equal to Ad Vd into 1 plus 1 upon rho Vc upon Vd, we get this output voltage Vo becomes equal to 100 Ad into 1 plus 1 upon 100 into 1000 upon 100, that is equal to 100 Ad into 1 plus 0.1 microvolt. In the first case, output voltage Vo was equal to 100 Ad. Now it is 100 Ad into 1 plus 0.1. So this output voltage will differ by 10%. Inside the bracket we have 1 plus 0.1. So it is increased by differ by 10%. In next question, part B, if we have rho equal to 10,000, then in a similar manner we find the output voltage for two cases. In first case, output voltage comes out to be 100 Ad microvolt, and in second case, output voltage comes out to be 100 Ad into 1 plus 0.001. Now for these two measurements, the difference is only 0.1%. So as common mode rejection ratio rho increases, the difference of measurement reduces very sharply. In the first case, the difference was 10% when rho was 100. When rho become 10,000, this difference reduces very sharply up to 0.1%. percent.